Statistics are random variables, and as such, they have distributions. Now, the distribution of a statistic is something that we will refer to as the sampling distribution of the statistic. And the sampling distribution is just a way of telling us we're talking about the distribution of some statistic. Now, sampling distributions are going to be the key for understanding statistical inference. The idea is that we're going to be able to make use of the distributions that statistics have in order to quantify our uncertainty around statistics, and ultimately, using those sampling distributions, we're going to connect the values of statistics that we actually observe in the samples that we take to the values of parameters in the population. And the parameter values are going to remain unknown to us, but because they're going to be connected through the sampling distribution, we're going to be able to make firm statements about their likely values, about how certain we can be about those values, what our guesses might be, and so forth. But this all hinges on us understanding the sampling distributions. So the sampling distribution is the distribution of a statistic when they are regarded as random variables. If we think about our statistic as being a process or a mathematical function, those are always random. And when we think about the randomness of those statistics, the distribution that characterizes that randomness is referred to as the sampling distribution. So, the distribution of a statistic. All statistics are random, and the randomness arises through sampling variability. Every time we take a sample, we get a different set of observations. Those different sets of observations cause the values of statistics to be different, and so statistics are actually going to be random. The distribution of the statistic is referred to as the sampling distribution. So before we have a sample taken, the value of our statistic is going to be unknown. We don't know specifically what the sample mean is going to equal. We don't know specifically what the sample maximum is going to be until we actually go out and take the sample. The specific value is going to end up depending on the specific sample that actually comes out when we've done our sampling. So once we do the sampling, we get some specific realization, and that's a realization of the random variable of the statistic. So this can be seen as a random draw from the sampling distribution. If you think about rolling a die, the result you get when you roll a die is a random draw from 1 to 6, where each outcome is equally likely. Every single time you roll a die, that's what you're seeing, is a realization from this random process. Every single time that we compute a statistic, we're getting a realization from the sampling distribution. Sampling distribution is the distribution of the statistic itself, and so every single time that we compute a statistic's value, we're going to be realizing something from our sampling distribution. So we can take a look at this example that we have on the slide here. And the idea is that on the left-hand side over here, we actually have our population distribution, right? And so we have this population distribution. It's going to be looking like this sort of curve shape here, right? Normally, we wouldn't know the actual population distribution. And so instead, what we're going to be thinking about is being able to draw samples from this distribution, right? And so over here, we can see that we take sample 1 and we get a 5, 7, 5, 6, 6, 7, 10, 10, 7, 11. Okay? And so each one of these values here is going to be drawn out of our population, right? And it's going to be drawn at random from the values of the population. But of course, we're able to take more than just our single sample, right? So at least in theory, we could have observed sample 2 here, right? Or sample 3 or sample 4 or sample 5. And anything that we compute from these samples are going to be different depending on the specific realizations that we actually get from the sample, right? And so if we think about, for instance, drawing the maximum value based on our sample, right? And so we can actually come to our population here, and we can see that the real maximum value is going to be somewhere over around 20, right? But that's not guaranteed to show up in any sample that we take. And so if we look at our first sample, we get a maximum value of 10. In our second sample, it looks like our maximum value is also going to be 10. Over in sample 3, right, we get this larger maximum of 15. And then in sample 4, it looks like it's going to be 14. And then here in sample 5, it looks like it's 13. Okay, and so each time that we take a sample, we're going to get a different maximum value, right? And the maximum value is random because it depends on the specific sample that we've taken. If we took a different sample, we're going to get a different maximum value. Now, the key thing to note is that if we start to characterize the distribution of the maximums, then we start to think about the sampling distribution. And so what we have going on here is this distribution that we've just introduced, right? This distribution is itself going to be the distribution of the maximums, okay? And so when we're thinking about sort of what we're actually observing over here, right? This is if you were to take the samples drawn, compute the maximum, and then do this over and over and over again, we see this sort of distribution emerging, right? And it looks sort of somewhat similar to the distribution that we have on the left-hand side over here. But the key thing to note is that it does not nearly go down as low. It's very unlikely that we're going to get a maximum value of around 0, right? And instead, our maximums are going to be centered more around values of 10 or similar, right? And so we're sort of pushing everything up a little bit. But this distribution here, if we actually knew exactly that this was the curve that we were going to be looking at for our sampling distribution of this statistic of interest, right? Then what we could say is that every single time that we take a sample and we compute the maximum, what we're doing is we're actually drawing a value out of this distribution. So it's not the population distribution, that's on the left here. They're different distributions, but as soon as we are realizing some value for the maximum, we're going to get a sampling distribution that looks similar to this. Now we can also think about, well, what if instead of the maximum, we took the minimum of the sample, right? And so now we've sort of split this column over here, right? And down in the bottom, we have the sampling distribution for the minimum of the sample. The sampling distribution for the maximum is still shown above. And we can see specifically, right, if we're looking at the values along the x-axis here, for the minimum, the values are going to be 0, 2, 4, and 6, rather than, say, 10, 15, or 20, right? So the maximum values are going to be bigger. That makes sense. The minimum values can go down really low. We also see that it's sort of a more smooth-looking curve, right? So it's sort of less, it has less of a long tail than the maximum does. And so the distributions here are different from one another. And that's because it's a different statistic. Every statistic is going to have its own sampling distribution. Neither of these sampling distributions is going to be exactly equal to the population distribution, right? And we won't ever know specifically what is this population distribution. We're never going to get to see that information in practice. But it's important to recognize that from this population distribution, and then from a statistic that we're interested in, right? So whether that statistic is the maximum, whether that statistic's the minimum, whether it's something else that we haven't looked at here at all, right? If you combine the population distribution with that statistic, then it's going to give rise to some distribution. And that distribution is what we call the sampling distribution, right? And so this is going to characterize the random behavior of either the maximum or the minimum from our samples that we can draw. Okay, so why do we care? What is the importance of these sampling distributions? And the idea is that sampling distributions are going to capture the uncertainty that is intrinsic to statistical inference. Every time that you take a sample, you're going random draws into that sample. And so there's some level of uncertainty that we will never be able to remove, right? It's always going to be there. We're always working with uncertainty in statistics. And sampling distributions are going to capture this innate uncertainty and allow us to actually discuss the levels of uncertainty that arise in this context. So the uncertainty is going to be unavoidable. You're never going to be able to get rid of uncertainty. It's always going to be with us in statistical inference. The sampling distribution specifically captures that uncertainty, right? So that's sort of a key component that it's doing. And so then using the sampling distribution, what we'll be able to do is actually quantify our uncertainty. We'll be able to start making probability statements about our uncertainty. We'll be able to actually start to give ranges of values, right? We'll be able to do all of this stuff that communicates we're not certain about the answers that we're given here, but what we are able to do is say, how certain are we, or how uncertain are we? And combining this information together and then learning how to sort of operate under the framework of uncertainty is going to be very powerful for making decisions or drawing conclusions about the world around us. Right? And so we can make our probability statements. We can, again, take intervals. We can make specific quantified statements about the uncertainty that we're faced with. And so the sampling distribution is going to depend on the statistic that's actually calculated, as well as on the population distribution, right? And so when we think back to that example we were looking at, the maximum and the minimum had different sampling distributions because they're different statistics, even though the population distribution was the same. If we had looked at another population, the sampling distribution for the maximum and the sampling distribution for the minimum would have also been different, right? And so the sampling distribution depends both on what is the population, how does the population behave, but also what is the statistic that we're actually looking at here. So what's loading up right now is an interactive tool for getting us to start thinking about the sampling distribution. I would encourage you to go to the link provided and actually play around with this tool yourself as well. The idea is that this is really going to get us familiar with sampling distributions, population distributions, and understanding what is the difference between them. So the way that this works is that on the left-hand side, we're going to be able to specify our sample size, our number of samples, the population distribution, as well as the statistic that we're actually thinking about. Then over on the right panel, we're going to be able to see some different plots. And so the first plot that we're looking at is actually the plot of the population distribution. And so if we go in and we pick a different population distribution, the plot over here is going to change, right? So we can look at an exponential, a Bernoulli, a normal, a uniform, and so forth, right? We can take a look at whatever we want. The second tab here, if we click into it, is actually going to show histograms of these samples, right? And so what we're doing here is we're taking the population that exists and we're drawing samples, in this case, of size 30 from them. And so we draw samples of size 30, and each one of these different samples is going to have some histogram. And so here, right, we're looking at the different samples of size 30 from our normal distribution. These are just the different values that we're actually getting. And if we increase, say, the number of bins here, we could increase this up to 10. You'll see a little bit more resolution in the plots that you're looking at here, right? But we're just seeing at what are the actual values that we've observed in our sample of size 30 from this normal distribution here. The sampling distribution is going to be the distribution of the summary statistic that we're calculating. So I take my sample number 14 right here, and I calculate the sample mean. And if we take a look at the sampling distribution, then we can see that we just get one plot because we've done sort of 1,000 times, we've repeated through here, and we've looked at what's the mean of each one of those 1,000 different samples, okay? And so what we're seeing here is the distribution of the summary statistic for the mean based on samples of size 30 from a normal population. Right, so this is our actual sampling distribution. If we change the statistic we're looking at, so instead of looking at the mean, we look at the maximum, right? The plot that we'll actually be looking at for all of our values, so for the population, it's not going to change, right? For our samples, it's not going to change because the statistic is not involved here. But for our sampling distribution, we're going to be looking at a different plot here, right? Same thing if we flip this to the minimum, right? Now we see we get some negative values coming out. Or if we go to the median, right, then we'll be looking at a different value here. Now, if we were to, instead of looking at a normal population, we could think about a uniform population, right? And here our samples are going to look a little bit different, right? Because now we're drawing from a different population. Okay, and so the key thing for us to be thinking about with this, and again, I would encourage you to play around with this sort of app in your spare time, but is that we have our population distribution. This is the distribution of how the trait is actually distributed out in the real world. If you could observe every single entity that exists, you would see the population distribution. Okay, the samples are going to be the individual observations that you actually make. Every time that you draw a sample, in this case of size 30, it's going to look at a different sample that you get, right? Our samples are random. There's going to be sampling variability here. Sometimes they're going to look super uniform in this case. Sometimes they're not going to look very uniform, right? But then each one of these samples, we can calculate whatever statistic we care about, right? So maybe just the sample mean, and that's going to give rise to our sampling distribution. So the sampling distribution is going to be the distribution of the sample mean based on samples of size 30 from our uniform population. Understanding the sampling distribution is going to be the key for us to actually conduct statistical inference going forward. So understanding where does the sampling distribution actually arise from? Where is this randomness coming from? What is the difference between our population distribution and our sampling distribution? Actually sort of coming to terms with all of these different concepts is going to be the thing that allows us to actually start doing statistical inference. That's going to be allowing us to actually draw conclusions about population parameters or make very quantified statements about the values of parameters in our population. And so the sampling distribution is really going to be the key that links what we're doing with our samples to what we want to know in our populations.